Your test will be 1 week from Monday, so I'll see what order I cover things in, but we're gonna at least have 5-1 on there. I think I put a little bit of 5-2 on there, so we'll keep looking. I'll tell you on Monday, I guess, when we know better. But I'm ready to answer any of your questions if you have any.
Okay. I have one on Weber, number 2.
Get one line. You have it, or am I pulling it up?
I found it.
What a gal. Okay, kind of read it to me and I'll take my way through it.
A fence is to be built to enclose a rectangular area of 310 square feet. The fence along 3 sides is made of material that costs $3 per foot. And the material of the 4th side costs $15 per foot.
Ooh, that's gonna be the pretty side. Okay.
Find the dimensions of the enclosure that is most economical to construct.
Minimize the cost of a rectangle. Minimize the cost of putting a fence around a rectangle if you know the area of that rectangle. So those are all per foot type numbers. So we've got to use variables for the number of feet. So let's say I've got L feet here and W feet there. So according to the picture, if I add up all my costs, I have 15L plus 3W plus 3L plus 3W to be my total cost. So if I add all those like terms together, it is going to give me the cost function to be 18L plus 6W. And we want to find the most economical one, so we want to minimize this function. So that's the thing we're going to take derivatives of, but you see it's got L's and W's. We need to get rid of one of them. So find a number that we haven't used yet and write a side equation. So here's my 310. That's square feet. So that's an area measurement. So my side equation is the area of the rectangle. L times W is 310. We're going to use that to get rid of either the L or the W. So how about I solve that for W in terms of L, and I get that W is 310 divided by L. So we're going to put that right here. And then my cost function is nothing but L's. So cost is 18L plus 6 times 310 divided by L. Let me go ahead and multiply that out and write that as L to the -1. And so our cost function looks like 18L. Let's see. There's the 6 times 0. There's the 6 times 1. And there's the 6 times 3. Okay, this is where you take over. Take the derivative and see if you can find the critical number. And I'll just stand here and stare at you menacingly. Even if this is not the exact numbers you have in your problem, I want to see if you can get the critical numbers. Yes,
Is that first equation?
yes, because that's where we're putting the fencing.
Oh.
So it's the perimeter with the numbers attached to them for the dollar amounts. So if you minimize fencing, that's perimeter. If you maximize area, then of course it's length times width. Perimeter is just the length around. I don't think you get nice pretty numbers, do you? Get your derivative to be 18 minus 1860 L to the -2. Let's put a 0 over here, and let's write that as over L squared. But it's only the 1860 that's over the L squared. Then I'm going to take the negative number to the other side, make it positive. Multiply both sides by L squared. And then divide by 18. Maybe I can reduce that a little bit. Let's see, I can divide both of them by 6. 3 times 6 is 18. And 6 times 10 here. And then here, 3 times 6 is 18. So L is going to be the square root of that number. Second derivative test is going to tell me if I have a max or a min. The derivative of that is 0. The derivative here is positive 2 times 1860 over L cubed. And that is a positive number, especially when I plug that in. So if the second derivative is positive, do we have a max or a min? Second derivative is positive. It's a min. That's what we wanted, right? So we have a min. And then just answer the question, do we want the minimum cost or do we want the dimensions? Okay, so we got L. And then here is W. So dimensions, minimize, cost are L is square root of 310 over 3. And W is 310 divided by square root of 310 over 3. Isn't 310 divided by the square root of 310 the same as the square root of 310? I think they're the same number. So again, it's a square. Both things in width. Do that too fast? So state your objective. Try to write your objective function in terms of variables. If you've got too many variables, find a number and write a side equation. Substitute that extra number in and then do the calculus. And take a brief minute and answer the question kind of in words. Anybody else? Anybody? Anything else? When are these due? They 16, so I'm giving you all kinds of time. So none of you have started it yet.
I actually have to go. I have to put it down already.
Okay.
just kidding.
Just kidding, just kidding. All right, you have to read it to me.
Okay. The top and bottom margins of a poster are 6 centimeters.
Okay, so I'm making a rectangular poster.
Yes.
The top and bottom margins, 6 centimeters, okay?
And the side margins are 7 centimeters.
All right,
The area of the printed material
I guess it's gonna be in here.
is fixed at 386 square centimeters.
Right, it's that part.
Find the dimensions of the poster with the smallest area.
Okay, so we'll find that and that. My objective is to minimize overall area. Minimize the overall area. So it's a rectangle. Let's grab an L and a W again. Make L be this length and W to be the whole thing there. So our objective is to minimize area is equal to length times width. So now we need a sine equation that's going to take care of my extra variable. And it looks like the sine equation is going to involve the area, because it's centimeters squared, of the printed material. So we've got to use those margin lengths to get an expression for the printed material's dimensions, and then compute the area. So here's our sine equation. The area of the printed material is 386 square centimeters. So what's the length of the printed material after you take the poster length and move in the 2 side margins? L minus 14, very good. Come in, come in. All right, now do the same to give me the width of the printed material. So W minus the 12, gotcha. Pick a variable and solve for it. I don't know, doesn't matter. I'm gonna go ahead and solve for W. So let's divide by this stuff. 386 divided by L minus 14 is W minus 12. And so add 12 to both sides and that will be W. Okay. We can plug that in where the W is and then simplify that enough so that we can take the derivative. We're plugging that in right here. And now my objective function looks like this. Length times width. So I'm going to go ahead and send that L through there, and then we'll take the derivative. Probably going to have to use the quotient rule there on that first bit. I have 386 L divided by L minus 14 plus 12 L. So here's where I want to see if you can find the critical numbers. Do your quotient rule here. Here, I'll do this part. The second term is 12. Do the quotient rule, see if you can find the critical number. We'll see how long it takes, or how long I can go without multiplying it up to 14. Right, did you get that as your derivative? So I'm gonna put a 0 over here, and I'm gonna take this fraction because it's negative and move it to the other side and make it positive. So put the 0 there, move that side over, so let's just leave this 14 times 386. All right, so we'll stop for a bit and let you guys catch up and see if you can figure out the next few steps. So here's what I'm hoping you did. Multiply both sides by L minus 14 squared. Then let's divide by 12. Let's see, 12 is even, so let's take out 2. 6 and 386 are both even, so let's take out another 2. Times 1, that is 18. So I have 7 times 193 divided by 3 is L minus 14 squared. 9, 10, 13, none of those numbers are divisible by 3. Yes,
Wouldn't that 12, when you move it over to the other side, wouldn't it become negative?
no, because I'm dividing both sides by 12. I'm not subtracting, dividing,
Why would you divide it?
because it's not added to anything. Right, I got a 1 over, I got that over here, so it's right here in front, right, it's multiplied.
No, in the last step, when you move it from the addition.
No, I moved this one over.
Oh,
I moved the negative
okay.
term over. I moved that over. So the wrong 12, huh? Okay, so I tried to reduce to see if I had any perfect squares in there, and I don't. I have a bunch of numbers that aren't divisible by each other. And so I guess the next step is to take the square root. I don't know how big this number is. I think it's bigger than 14. Don't you? Yes.
Never mind.
We'd like to go back and point something out, or you can tell me where my mistake is.
What happened to the L on the, whenever you divide it out, or you multiplied out the L, the.
Well, this one's gonna give me the same as that one,
Divide out.
so those add to 0. So I just have 14 times the 386, and it's a negative 14. So let me go ahead and multiply this out. 3 times 7 is 21. 7 times 9 is 63. 2 more makes it 65. 7 plus 6 is 13. All right, let me see how far that little screen will go. Maybe one more little bit here. So I get the square root of all of that. 1351 over 3 is L minus 14. So here's where I don't know whether to take the plus or minus root, because you're gonna have to figure out how big that number is. So let me kind of estimate how big that number is, because I gotta add 14 to it, and I need to make sure I can get a positive number. So if this is bigger than 14, then I don't want the negative. So let's see, 3 goes into 13, well, 4 times, leave me 120, leave me 15. So anyway, it's 400-ish. Square root of 400 is 20, right? So this I'm gonna take the positive square root. I can't take the negative square root, that's in the neighborhood of 20. Because now I'm gonna add 14, and I need my dimensions to be positive numbers. So there's my L. And again, it looks like it's too messy to do the second derivative test. And here's how we get W, by putting L in there. So it's going to be mucky, maybe cut and paste. So dimensions are L is equal to that number. Square root of 1351 over 3. Plus 14. And W is equal to here, I'm putting it in here. 386 divided by square root of 1351 over 3. Plus 14 minus 14, so those will be gone. So there's our number right there. Oh, I forgot the plus 12. There we go. I know it. Okay. You got some really crappy numbers, don't you? Don't worry about numbers. Don't worry about numbers. Put some numbers in that. There they are right there. Hard to enter in it. Makes you an expert web word enterer. Cut and paste, cut and paste.
Don't be excited to do, I just have 3,000 attempts on.
Okay. Still typing? So I kind of want to use the rest of class then to talk about section 5.1. All right, I gotta finish it up. We started it, talking about antiderivatives. And so we were writing down all the rules that we already knew. So what we're looking for is an antiderivative of a stated function f. So an antiderivative of the stated function, little f of x, is going to be denoted with capital F of x, where if you take the derivative of capital F, you get back little f. And our notation for that was, we have this little integral sign here. Then we put the function whose antiderivative we seek right here. Then we close it off by telling you the name of the variable right there. So you read that as the integral of f with respect to x. And then you get this antiderivative here. And then to make it the most general antiderivative, since the derivative of any constant is 0, then I tack on the constant, and I usually use a capital letter C for that. I'll show you why we use this notation, hopefully today, we'll see how far we get. But what we tried to do is write down a bunch of rules for finding antiderivatives. Right, so if I said what function has as its derivative 5, what would you tell me? 5x, if I'm talking about x's, right? If I'm talking about t's, you'd say 5t. Any constant I call out has as its antiderivative that constant times the variable. So let's make that our first rule. So our rules for finding antiderivatives. The first one was that the integral of any constant, I'll use the letter k for that, with respect to x, is just going to be that constant times x. And then you get the other constant that we call the constant of integration. So what did I take the derivative of to get 2x? X squared. So what am I taking the derivative of to get x? There you go. The integral of x to the first power was 1/2 x squared. As the derivative of the x squared will give you the 2x, multiply it by 1/2 gives you back x. Now, there's no reason to write that as its separate rule. We had a rule in general for any power. How is the power of the antiderivative compared to the power of the function you're finding the antiderivative of? How are these related? n+1, right? So we put the new power up here. And then if I were to take the derivative of this as it sits now, I would get an n+1 here, x to the n. Well, I don't want the n+1 there, so I have to divide by the n+1. So that's our power rule for antiderivatives, except it doesn't apply when the power is a -1. If this is a -1, I don't want to ever divide by 0. But then I recognize that if x is -1, then that's the same as 1/x, and I know a function whose derivative is 1/x. What function is that? The natural log of x. But then remember, we need to make this have the same domain as this. So we put this in absolute value bars so that I can have positive and negative numbers represented by that x. We said the derivative of e to the x was e to the x. Let's even go more general. What's the derivative of e to the 5x? 5e to the 5x. So if I stick another number next to the x in here, let's just call it k, where k is a number, then the derivative of that is itself, but I get a k down in front. Well, I got to take care of that with the antiderivative. I get itself, but now to take care of the k that would show up in front, we divide by that number. Then we had our 6 trig derivatives. The derivative of sine is cosine. So the antiderivative of cosine is a positive sign. The derivative of sine is a cosine. The derivative of cosine is a negative sign. So if I just integrate sine of x, I should get a negative cosine of x. Derivative of cosine is negative sign, so that takes care of the negative. Let's see, the derivative of tangent is secant squared. So if we find the antiderivative of secant squared, we should get a tangent. What's the derivative of secant? secant x, tangent of x. So the antiderivative of that product give us a secant of x. Okay, I've got two more trig functions. What's the derivative of a cosecant? A negative cosecant cotangent. So if I move the negative to the other side, the integral of a cosecant of x cotangent of x is a negative cosecant of x. So sine, cosine, tangent, cosecant, we need a cotangent. What's the derivative of a cotangent? Negative cosecant squared, so I'm gonna move the negative to the other side and say that the integral of a cosecant squared is a negative cotangent. Good? Those are all the functions we know. Oh, we've got to know a couple of inverse trig functions. What's the derivative of an inverse tangent? One over 1 plus x squared. That is the derivative of a tangent, so the arctangent. So the antiderivative of that is arctangent. What's the derivative of an inverse sine look like? 1 over the square root. By the way, 1 minus x squared. So if I see that in my integral, that's an arc sine. The arcsecant had the x in front of the minus sign, and it also had an x out here. And we didn't need an arc cotangent or an arc cosine or an arc secant because their derivatives just had negative numerators. Now, when we learned derivatives, when we took derivatives, we were able to ignore numbers out front. Like if I'm taking the derivative of 8x squared, I kind of ignored the 8 and took the derivative of x squared the way I normally did, and then I put the 8 back on. We do that with antiderivatives as well. If I have a number here, some constant times a function, and this is seemingly in my way, I just slide it out of the integral sign. And then put the number back on after you find the antiderivative. With derivatives, we were able to do things term by term, through plus and minus. We can do that again with antiderivatives. If I've got several things added together, I do each one individually and then add the antiderivatives together. So the integral of the sum is the sum of the antiderivatives. We don't have anything yet analogous to a quotient rule or a product rule or a chain rule. So if we've got stuff that's multiplied, we have to multiply it out first so that we have a sum. If we have stuff that's divided, if there's just a single term, we divide it out, make separate functions. But we will learn how to do more composite functions in section 5. So I wanted to use the rest of the time practicing these. And I sent you a little handout with a bunch of integrals on them. Let's see how many of these we can do. Let's see how much of this shows up on my. All right, and now I have no room to write. All right, here's the examples. So what you should do is put these rules kind of on a note card or something and have them next to you while you're using them until you have them all memorized, and then you throw that note card away just like you know the derivatives already. Kind of got a little rusty on these over here. Okay, so our first example is to find the antiderivative of 3, what is that, an x? 3x minus 2 e to the x minus 4 dx. So what I said here, these two can go together. It says I can make 3 problems out of this. I can write that as 3 times the integral of x and do a power rule right there. I can pull out the minus 2 and then find something whose derivative is e to the x. And then I can leave the 4 alone because I have a rule that tells me what to do with constants. I'll write that down now, but eventually we'll get where we do that part in our head, just like with derivatives. We do things term by term through plus and minus signs. All right, so over here we said that the integral of x was 1/2 x squared. We'll save the plus c for the very end. So here I have 3 times 1/2 x squared. And then here's the easy one. The derivative of e to the x is e to the x. The integral of e to the x is e to the x. And what about the last one? What did we take the derivative of to get a 4? 4x. Now each of these has a constant of integration. We add them all together and get one constant of integration. And if you want, you can write that as 3/2 x squared. There's nothing to simplify that. But then you can make a quick check to see if you have the right function, right? You just take the derivative. The derivative of this should give us that. So when I take the 2 down here, I just get an x, so I have 3x. Derivative of e to the x is e to the x, so that's that. Derivative of 4x is the 4. Now, in the next one, we've got some messier exponents. Just take your time and you can handle them. And when you have the radical sign, make sure you just replace the radical sign with a fractional exponent. So in the next one, I've got x to the 3/2 minus 4x to the -1 plus the square root of x. So for the first one and the last one, you're going to use the power rule, but not for the x to the -1. Because remember, x to the -1 has its own rule. So let's write 3 integral signs, x to the 3/2 dx. And then pull out the -4. And then we integrate x to the -1. And now let's write the square root as x to the power. What's the power when it's a square root? A positive 1/2, right? Okay, so like I said, the first and the third ones are just the power rule. So you've got to add 1 to the power. How much you get when you add 1 to 3/2? 5/2? What was the function whose derivative was x to the -1? Natural log of the absolute value of x. And then out here at the end, we have to add 1 to 1/2. Tell me what you get when you add 1 to 1/2. 3/2, so we have 1/3/2. And tack on the plus c to get the general antiderivative. Now let me simplify that. Dividing by a fraction is equivalent to multiplying by its reciprocal. So instead of writing 1/5 halves, let's write 2/5. 2/5 x to the 5 halves minus 4 natural log of the absolute value of x plus 2/3 x to the 3 halves plus the constant of integration. And then make a quick eyeball check to see if when you take the derivative of that, you get back what we started with. All right, quick check. 5 halves times 2/5 is going to give me the 1. Take 2/2 away from that, and I get 3 halves. Integral, the derivative log of x is the 1/x. And here the 3 halves times 2/3 is again 1. Take 2 halves away from that, and you get a 1/2 power. That hurt it all to check your answer, your differentiation. All right. Number 3. We're going to integrate the cosine of x, or 3 times the cosine of x, minus 2 sine of x dx. So I'm not going to write that in between step. We're going to do that part in our head. What function has as its derivative cosine of x? So this will give me 3 sine of x. Okay, now I've got the sine here. What do we take the derivative of to get a sine? A negative cosine, right? So this is going to be -2 times negative cosine. We can go ahead and put the 2 negative signs together and get +2. As I can see on the end up there, that's a better one. Go through there quickly and take the derivative and make sure you get back what we started. Okay, next one. Three times the integral of secant squared of x. It's a quickie. What is the integral of 3 secant squared of x? 3 times the tangent of x. Think backwards in terms of taking derivatives. What did I just take the derivative of? Well, the answer is it's tangent. The next one's a quickie. Cosecant times cotangent is in your integral sign. What has that as its derivative? Negative cosecant. There's no pleasure in doing these. Boom, you're done. Write it down, done. Write it down, done. Okay, so let's be careful here on number 6. Let's see if I can still see this on the screen. Nope, dispute it, dispute it, dispute it. Make my 6 over a bit. We're integrating e to the x over 2 minus e to the 4x. We're using the e to a constant times x rule. Or you can always just take the derivative and undo the number you get when you take the derivative. So if you were to take the derivative of e to the x over 2, what would you get? The derivative, not the antiderivative. X over 2 is just 1/2 x. You'd get a 1/2 e to the 1/2 x. So how do we get rid of that 1/2? Put a 2 there. So the integral of e to the x over 2 is 2 e to the x over 2. Remember, we divide by whatever number is in front of the x. Dividing by half is the same as multiplying by 2. So what's the antiderivative of e to the 4x? 1/4 e to the 4x. Okay, number 7 is a quickie, kind of. Got a 3 up here. Don't let the 3 throw you off. But which one of our functions has a derivative that looks like this without the 3? The inverse secant, right? So we have 3 times the arc secant. Take that 3 out of the way. That's the arc secant of the variable x. Let's see. Let me got that in there. There it is. All right, let me go backwards again. All right, here's your next one. We've got 3x squared plus the square root of x minus 1 over x. Get that while I erase. Usual, think of the square root of x as x to the 1/2. Okay, so what do we take the derivative of to get 3x squared? Just x cubed, right? You recognize the derivative already? Just go ahead and go to x cubed. Now here we're going to use the power rule. You add 1 to the power, divide by the new power. I'll go do that in the next step. And what did you do with the 1 over x at the end? There you go. You get the plus c. All right, so now I'm going to do the arithmetic. 1/2 plus 1 is 3/2. And so I'm dividing by 3/2. Let's flip it over and put a 2/3 here. Okay. Get the hang of putting the plus c on there. I don't take points out for it. They do charge you $1 for each one you put in. You can always Venmo me the money at the end of the semester. Okay, the next one. We got time, right? I got about a minute. I want to show you what happens when you've got the x in the denominator. We've got to rewrite things just the way we did when we did derivatives. I can't just go down there and do the power rule on that x that's in the bottom. I have to move it up first. So we have to rewrite that as 3 times x to the -2 and then do the power rule. And then if this 3 bothers you, pull it out as a factor of 1/3. The x squared is already on the top. Now, both of those are power rules. Add 1 to the power, divide by the new power. What do you get when you add 1 to a -2? You get a -1. So this becomes 3x to the -1 over -1. And here's the 1/3. Let me pull it out of the way. And now what's the antiderivative of x squared? So I get another 1/3, and then x to the +3. And then the plus c. So now let's rewrite it. This becomes a -3 x to the -1. And I think it looks better if I write it as -3 over x. And that times that gives me -1/9 x cubed plus c. So move things up, write them the way you do when you first learn derivatives. Something times x to a power plus something times x to a power. And if you kind of look ahead on number 11, look there at number 11, you got to break that up into 2 fractions. Number 13, you got to multiply it out. And then you can integrate it. We'll finish those on Monday. Monday. And then we're looking at our test to be 1 week from Monday. Good? So I'll figure out on Monday which order I want to cover your sections in. What happens if you took the derivative? You get itself times the derivative of the exponent. So the derivative would have a 1/2. Thank you. So you want to get the 1/2 out of it. So you divide by 1/2. But dividing by 1/2 is the same as multiplying by 2. Okay. So in general, if you have a number up here, you got 1 over that number here. So 1 over 1/2. Don't trip.
Question about, like, how to